Okay, this is our last regular lecture of the semester. And let me draw your attention to the bottom of the screen here. Um, Tomorrow, our office hour, mega office hours, double the amount of time from 9 until noon. And they're in room 158 in the physical sciences building. So I know that's a little tricky for some people to find. What are those dorms right next to physical science? That's not Libra, is it? That's Libra? Yeah, okay. So it's right, the counseling center is right next door and stuff like that. So yeah, mega office hours. Um, for those of you that are newbies here at UCF, tomorrow is UCF Study Day. And so for those of you that are new to, you may take this attitude maybe. For those of you, I see somebody over here in the middle go, yeah, that's like you, that's like you. I see, but I think probably maybe there's some people that will maybe take a little different attitude. Uh, yeah, we got a guy up here in the front going, yeah, better not. But hopefully you'll have something like this going on. In other words, come to office hours with Dr. B, 9 a.m. to noon, and then mosey on over to the study union. Here's the specs for those of you that want to get in an extra 2 hours. And Shai is going to, you have a regular SI today, right? Okay, so regular SI today, as always. And then this one tomorrow, and you're going to record it, correct? Okay, she's going to record it. And I don't know, she's going to post a link to her Google page for her review sheet, all that stuff. So definitely try to do that. Now that's not interfering with my office hours, and it's not interfering with anybody's, what do you call it, SSG. By the way, there's some Tuesday SSGs that are running this afternoon, I believe, and tonight. And when I got up at 4 this morning so I could get everything ready. I've been running around like a crazy man. You may be thinking to yourself, Dr. B, you're up to your mischievous tricks as always. But I've got a huge amount of things that I've been doing, really running hard. And I was up at 4 this morning, and the SSGs were not full. Not all of them anyway. Some of them were. So I don't know if they are now, but if they're not, you can go in and snag a spot. Okay, the bonus mega review in web courses that I promised to you. I thought I would get it going Saturday or so, but I didn't get it going until last night. But it is a kind of a nice little study tool, and I've set it so that it's due. I think I set it due next Monday night. So, and I think you can actually go in there and hack at it, and go ahead and do that. Also, we're going to be doing some regular clicking today. A couple questions. The last regular clicking of the semester, and then after I finish my mini lecture on the periodic table, you will have a review session. With a review session handout, and you'll do that on the iClicker as well. We'll get that started in a few minutes. I want to look at this particular problem from homework 20, and just so you know, I got alerted last night. I was extremely tired, and so I didn't really sort things out. But this problem, and then one of the brain burners at the bottom of the homework, I'm just ready to send in bulldozers to the Canvas computer system because it's burning my grits. Anyways, the philosophy on this one, and we need this, so you should consider these to be your beginning notes of today for our mini lecture. An oscillating system, simple, a mass on a spring that is stretched out from equilibrium at x equals 0 all the way out to 3.3 centimeters or 0.033 meters. The potential energy at that point, you can compute 1/2 kx squared. And that's going to be so many joules of potential energy. And at that point, you let it go. So you pull it out there and you hold it, and then you let it go. So it starts with 0 kinetic energy, maximum potential energy. And so what I had asked you was, what was its, I think, maximum leftward momentum? And this one was different, for this particular instance. Oh, also this one was not calculating properly. I have fixed that, and also I've put a hold on homework 20, and I'm going to release homework 20, and everybody's going to have at least another 2 or 3 attempts on it. I'll try to do that this afternoon. You can mess around with it. And I'll make that due Friday, so you have plenty of time on that. But anyways, I got to get this part calculating properly. This is how you do it. You figure out the potential, the spring potential energy at maximum extension, and then you say to yourself, okay, when my mass gets back to the equilibrium point, I've converted all that potential energy in the spring into kinetic energy. So that's 1/2 mv squared at equilibrium. All right, and so what we've got is, all right, 0.0973 a kilogram meter squared per second squared of kinetic energy at equilibrium. And that's 1/2 mv squared. So now you can figure out v squared. The mass was the same for every attempt. The spring constant changed. I think that's the only thing that changed. All right, the max extension was 0.033 meters for each attempt. All right, so this is for the instance that I had. So you figure out v squared, and that works out to 0.778. Verify me if you want. Anybody verify me on that? Nobody verifies me? Okay, just multiply that by 8 and you'll get it. And then, so you square root that and you get 0.882 for the speed. Now you're going left, but this is at least the speedometer rating. If you were going to write a velocity, you would put a minus sign to indicate left. And the momentum is just 0.25 times that, and that works out to 0.221. And so the answer, I think the question was, what is the maximum leftward momentum? So for this one, this is not the last step in your calculation. What you would type in is negative 0.221, and then hit your submit button. Now, as I said, I'm going to re-release this tonight sometime after I fix all the nasty Canvas. I'm really getting sick of Canvas, especially these calculation problems. I try to get them fixed and they don't stay fixed. Did you have a question back there? What's that? Yeah, I think it asked for leftward, as I recall. Yeah. Yeah, I know. There's always problems with those brain burners. The only way I can get them to work is if I make a multiple choice. It's just, anyways, I'll get that squared away for you guys tonight. Anyways, now make sure you have this down. MV is 0.221 for maximum rightward, and then maximum leftward would be negative 0.221 kilogram meters per second. And what I want to do now is draw an ellipse on phase space for this spring oscillator. All right, don't talk over me there. Okay, you're rumbling way too loud. All right. All right, so what we've got in phase space, where the momentum in the x direction, p subscript x, is on the vertical axis. So this is an abstract graph. It's not a map that you can look at and walk to, but it's an abstract graph. X is on the horizontal axis. It's a periodic behavior, so it's going to be a closed path, and it will be elliptical. Maximum rightward is up here, so this should be 0.221 in the vertical axis. Maximum leftward means negatory, that's down here. Negative 0.221 for the momentum, p subscript x. And then maximum extension, that's out here, positive 0.33. And in the problem that we worked on, the spring was off to the left. Okay, and so the max compression is over here on the left side, negative 0.33. It is symmetric. Here's a completely labeled version of it with units in phase space. This is called phase space. This is the phase diagram or the phase portrait. And they form an ellipse. And this ellipse is very good and helpful for us because it kind of defines the interrelationship between the dynamical quantity momentum and the spatial position marked in the x-axis. They are related for this system. They're related for any system, really, but for a spring oscillator, they correspond to an ellipse. Very easy to map out. Now, caveat, option or item 6. If I had drawn the block out a little bit further, for instance, to 0.048 meters, 4.8 centimeters, then the spring potential energy would be bigger. The maximum kinetic at equilibrium would be bigger. And the upper and lower values, the upper and lower bounds of the momentum would be larger as well. You'd be deeper in the negative for your leftward momentum and deeper or further in the positive for the upward one. So the ellipse would be bigger. So it depends on how you change things. All right, now I've got a question for you that I want you to, hopefully you've got your ellipse all labeled up. But if you don't, we are going to look at it again. And I have a question for you on the iClicker. So let's go ahead and start. And I want you to read this very, very carefully. Frequency BB. For an oscillating spring system, how do the position and momentum state evolve over time from the initial conditions 0.33 meter, 0.000 kilogram meters per second? In other words, here's your initial position on the phase diagram, right over here, the rightmost point on the ellipse. Now, if I'd started on the at max compression, we would have been starting over here. But I started here, and my question to you is, which of these three options describes what happens to the system over time? I want you to talk to your neighbor and think it over. And you SSGs, even the SSG leaders are going to be challenged by this one. It's not in your notes. It's something that hopefully you can decide by using these notes. How come you're sitting in the back row or in the second row? What's up with that? Oh, you know, Caroline was supposed to be the bouncer over on that side of the room, I guess. See? People getting out of line. 20 seconds. I'm very curious to see how you guys do. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Aha! Very interesting. A range of answers. Range of answers. We better do some explaining. All right? First part of the explanation is you start here, and after you start, you're actually going to move leftward. So your momentum is going to be negatory, so you're going to head down here. And that means you're going to go counterclockwise. Make a note of it. And in fact, what? Hey, that is count. All right. For those of you that voted correctly, I'll change the answer key on that one. You're right. Dr. B. Ooh, the majority of you got it right. It should be, yeah, it should be clockwise. And I've got it marked properly on the next slide. So here it is. And this is the upshot that I want to review with you. And that is that by asking this question, you can determine or visualize the direction of time in phase space. All you have to do is draw in some arrows. And here, let me just burn this one in. Go ahead and put a couple arrows in here. Let me burn another one in here. All right? And that is the direction of time on a phase space diagram. That is significant. Matter of fact, there is a lot more to a phase space diagram like this, but to visualize the direction of time, yeah, we want to know all about that, because time is really the deepest riddle of all. Not even Einstein could figure it out. But he could have done this, he could have studied this, I'm sure he probably did at some point. And if you asked Max Planck and Albert Einstein, they would have said, yeah, this is nice, direction of time, good, nice. There's also a lot more in a phase diagram. Let me ask you this. Here's another question. Oh boy, I hope I have this one keyed in right. For the oscillating spring system, what if we have a stronger spring, but we still release from 0.033 meters? Go ahead and vote. Think it over. How would it change? Or would it not have any change? Start at 0.033, no change. Oh, look at C. I guess you can figure out that C is not correct. So nobody better vote for C. Oh, I tell you, it's been a tough last few days. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Wow, very interesting. Here's the distribution of answers. And actually, D is completely wrong. It would change. What you would have is taller. And the reason for that is it's a stronger spring. So inch for inch, centimeter for centimeter, you're going to get more kinetic energy at the center if the spring constant is bigger. Now, I actually calculated it out. Here's what it would look like. Superimposed on the old one. So if we did, if we did 205 for the spring constant, it'd be a little bit bigger. Okay. And so it'd look about like this. These slightly different things. So let's do a recap. And this is what I want you to take away from this. Different initial conditions produce different direction of time and phase space. All right. And different dynamical states and different springs make for different ellipses. All right. So if you change the strength of your spring, nice. You get a different ellipse. Maybe taller. And then if you change your initial conditions to a different position, then everything's different. So it's kind of cool. Now, we're going to do a demonstration, and I'm going to record it on the podcast. I'm going to turn the lights up. Carolina, can you come on up? And Hector, can you come on up and do the video? I want you to really listen to a guitar. And great. And this is Carolina Rivera. And Hector, my faithful cameraman, is going to operate the camera, my camera. And this is going to be 1280p, so it's going to be really nice when we put it in YouTube. Okay. All right. Now I'm the director, so I get to say cut and all that stuff. All right. Now don't look at me. Look at Hector. Hector, get it going. All right. Yeah, go ahead and start. Now, what we're going to do, Carolina's going to play each string. And then, yeah, don't do that telephone. Did it start? I don't know. Is it going? I don't think so. Yeah, it is. It's a green dot up there. Right? Here, let me see it. Dude. There you go. Yeah, there you go. Yeah, this red dot.
Awesome.
All right. All right. Now we're going. All right. So what we're going to do, you got to hear this. She doesn't have an amp. All right. She's going to play each string, and then she's going to strum a chord, and then she's going to take one of the strings out of tune by uncranking it or cranking it a little tighter. I don't know, whatever she thinks is good. And then she's going to play that string again. And then she's going to try the same chord, and hopefully you'll hear it. All right? Then she'll retune it by changing the tension. And then, she'll strum that same chord again. Okay, go ahead.
So you start from the bottom, and this is a small E string. It sounds real nice and high. Then it goes to the B string, followed by the G string, the D string, the A string, and the big E. So I'm going to put down the A string. Or first, actually, I'm going to play the C chord, which is my favorite chord.
Excellent.
So then I'm going to put down the A string. So then I'll strum the C chord again.
Okay, enough. No, good. I don't want people start puking in class.
So yeah, obviously it sounds very different. Put it back up. Tune it.
I see somebody in the middle of the class go like this. It's hurting their ears.
Back up.
So it's back in tune now? Play that A string again by itself. All right. The chord sounds good. Play that chord one more time. Okay, can you play something beautiful, a song now? Just for a second. Lovely, thank you. All right, give Caroline a gigantic, Hector, thanks. Oh man, I tell you. Thanks, man. Carolina, thank you, thank you, thank you. Great. All right, now, my wonderful students, you may be thinking to yourself, Dr. B, what has a guitar got to do with atoms and the periodic table? All right, let's take a look at it. She is using, how do you say that name? Diodario. Okay. Okay. She's using Diodario nylon classical half-step trebles, strings. Okay. And so you can actually look up the specs, in which I did. You know, I even emailed the company, and the guy said, "Yeah, you could use this specs table, a little booklet." And what they do is, each string they rate in three different ways. First of all, the unit weight, and that's how dense the string is, how many pounds of steel or nylon or brass or whatever it's made out of per inch. Okay, so pounds per linear inch for the unit weight, and you can look up all this stuff on the second page and then following in this little spec sheet that they have on their website. Okay, for the string tensions. Another thing that is important, and you should make a note of this, is the scale length. All right, now that's also published in this booklet. And the scale length is basically the distance from the guitar's nut down to the bridge. So the bridge is down by the sound, what do they call that? The sound hole. And then the nut is up there at the end of the, what you call it? The what? Yeah, the head, what she said. Okay, I'm pretty ignorant about guitars, but I love them. I love listening to them. I wish I could play one. Anyway, so the scaling, so it just depends on what kind of instrument. If you have a classical guitar, then and that's a classical, right? Okay, classical acoustic guitar. 25 and a half inches is considered the standard for Diodario strings. Mandolin, which is a different instrument, 13, quite a bit smaller, 13.875. Hey, which one do you think is going to play at a higher pitch? The mandolin or the regular classical guitar? The mandolin, probably. And I looked it up for a super bass guitar. You know how long they make those? 36 inches. And it's just really long. Longer, lower frequency, bigger wavelength for the fundamental. Then the third thing that they specify is the actual note and its frequency in hertz. So for instance, middle C for their system, 261.6 hertz. Did you, Caroline, did you play, was one of those a middle C or? The C was a middle C. Okay, so and so when you were listening to that, you were listening to a lot of 261.6 hertz vibrations. Now, the physical factors are the tension and how heavy string is. You know, is it a light string or is it really thick and heavy per unit length, per inch? And that corresponds to the pitch, or that will determine the pitch, right? And here's another thing that I want you to think of, and I want you to make a note of this. Every pixel of of each string, you know, she has 6 strings, right? It's 6, right? And each string, you know, you think of each little unit of it as, you know, moving up and down at a certain, you know, in concert with its neighbors. And in concert with its neighbors, if it's well tuned, means you get 261.6 hertz middle C, or whatever the note is for that string. Okay? And each pixel with its neighbors is going to have its own ellipse in phase space. So different strings, different tensions, is like different spring constants. Right? Different forces. Different strums means, I should have asked you to do that, you know. If you have a really hard strum, it'll be really loud. But if you want to really have a soft, you know, low amplitude sound, you don't strum it as hard. So your initial conditions are different. And because of that, you know, how you play is going to be expressed with different ellipses. You know, which string you play and how you strum it. All right, let's get to the periodic table. And to think about the periodic table, let's go back to Professor de Broglie, who made this answer to a fundamental question. Why is an atom stable? Why don't the electrons just spiral down into the nucleus? And he said, well, if they have wave properties, they will be stable because they'll have constructive interference. So for instance, there's no real way to diagram the waves. This is like an idealization of an electron wave, but this has 4 squiggles. Here's the top. Here's the bump of the first squiggle. Second squiggle. Third bump. Or this is the bump of the third squiggle. And here's the bump of the fourth squiggle. And in between each squiggle, or excuse me, in between each bump, Anna, is a dip. Okay, so here's like a dip right in here. All right? And if you have exactly the right wavelength, said de Broglie, you'll have constructive interference. And only at certain altitudes from the atom, whether hydrogen or anything else, will you get constructive interference. Okay, so the wave interferes with itself, that electron. It's not a little planet. You can think of it that way, but you can't get a little teeny planet to interfere with itself. Only waves do that. And this is how nature selects very precisely which quantum orbits are allowed. They have to have enough diameter so that you get 4 full squiggles, or 5 full squiggles, or 6, or just 1 full squiggle, and all the way around. That would be all right. That would be constructive. All right. If you have 1 full squiggle all the way around, that's the ground state. All right. Here's another picture. And this shows a bunch of squiggles. 3 different sets of squiggles. And de Broglie said, you know, if it curves around just right, it'll constructively interfere. Now, we also know that that is what happens with a guitar. When Carolina strums the A string, it has a very specific size and a very specific tension. The forces are very well specified, and it has a very specific, you know, mass per unit length, so many pounds per inch, a fraction of a pound, they're not very heavy, fraction of a pound per inch. And all that's very well specified. And if you do that, you only get specific fundamentals and then the harmonics, the excited states above that, a little bit of that. And so for the A string, only certain frequencies, therefore only certain wavelengths. So just like the atom, if you have a hydrogen atom, only certain wavelengths will actually fit on a circular orbit. For a guitar, from the bridge to the nut, from point A to point B, slightly different. It's not circular. You're not going around in a circle, but you have specific limits, specific forces, and specific wavelengths. And those wavelengths correspond to the pitch that we think about. So these are the formulas that control all of that. De Broglie figured out this equation, lambda is equal to h over mv, or h over p, the momentum. And he said, you know, if you compute the wavelength and the mv and everything like that, it all works out perfectly for hydrogen. In other words, he was able to figure out the momentum, knowing the size of the electron, knowing the size of the nucleus. He could figure out, you know how far out you're going to be to get one full squiggle, two full squiggles, three full squiggles, four full squiggles around the proton and the nucleus. And when he figured that out, he was able to figure out exactly H alpha, the wavelength for H alpha from n equals 3 down to n equals 2. The same one that we saw. Now, we've talked about this already, energy levels, the countable energy levels, different altitudes, different orbits. We say that when an electron jumps from one orbit to the other, it never occupies anything intermediate, only n equals 3 or n equals 2, nothing in between. We call that a quantum leap. If it's going down to n equals 2, or if it's being bumped up, you can do a quantum leap upward too, if you get some incoming photons. All right, so those are quantum leaps from orbit to orbit. A quantum leap from orbit to orbit corresponds to this. In phase space, it corresponds to jumping ellipses. Go ahead and make a couple nested ellipses. Right? Two red ones. And one of them is cross-hatched, and then the other one is solid white. The small one is solid white, so it blots out the central area. Now the cross-hatched area is, in fact, the area of any ellipse in phase space is measured in kilogram meter squared per second. Okay, length, or the height is kilogram meters per second, momentum, and the width of every little pixel is meters. So the area is kilogram meters squared per second. That is angular momentum. Right? Quantum leaps from orbit to orbit correspond to quantum leaps from ellipse to ellipse, jumping ellipses. And here is what de Broglie and all the guys back then, about 90 years ago, figured out. That if electrons constructively interfere, then the change in the area from big to little, okay, so that's the cross-hatched area, only comes in bundles of H. In other words, Planck's constant. Planck's constant, which I mentioned a couple lectures ago, is measured in angular momentum. And Planck's constant is the one that controls the size of the ellipses. So if you're thinking about orbits and orbital radii, yeah, you can do that. And then you think about the energies. But if you think in terms of phase space, And what nature is doing, nature is jumping in finite-sized jumps. It's not going to select any other ellipse, Logan, other than the next one down. If it loses h in area, or 2h, or 3h in area. And for that reason, we say that Planck's constant is the one that controls the entire quantum world. That process of jumping ellipses that differ by multiples of h, that is called the quantization process. The quantum world is quantized. It is quantized in units of h, Planck's constant. And the ellipses in phase space only for true orbits only differ by h or 2h or 3h and so on. So it's possible, and matter of fact, Planck's constant is involved in every physical system, even large things other than atoms and nuclei. But because the wavelength of really large items like a paperclip, they're so small, the wavelength is so small, you can't really observe it very easily. Now, Planck's constant. Planck's constant controls which ellipses are jumped. The ellipses that are jumped correspond to energy levels and different radii. And the different radii correspond to different wavelengths. Okay? And the wavelengths are the ones that constructively interfere. Now, every element has a different nucleus. We talked about hydrogen. Hydrogen has just the proton. It's nice. That's all it's got. But helium's got 2 protons, so every electron's got twice the pull if it's orbiting a helium nucleus, right? And lithium has 3 protons in the nucleus, so it gets triple the pull. It's like different tensions in the guitar. Here's a picture of Professor Mendeleev, a Siberian guy. I don't want to show you the picture of when he was older because he looks like a homeless guy, which apparently was the fashion in Russia back in his day in the late 1800s. Anyways, here's a picture of him as a young man. He's the one that figured out the periodic table. And my wonderful students, what he figured out was that every column of the periodic table has similar properties. For instance, the far right column over here, these are called the noble gases. They don't make chemical compounds with anything. And Mendeleev figured that out. All these objects over here on the far left, these are considered very easily oxidized metals. Okay? And they're called the alkali metals. You can look it up on the periodic table. And the second column is alkali earth metals. And everything on this column has similar properties. The reason that they have similar properties is because their outermost electron has very similar wave patterns. The outermost, they all have different numbers of electrons, but the outer 1 electron, the outer 2 electrons, the outer 3 electrons, all have the same pattern, if spatial pattern, if you look column by column. And that is because each atom is like a guitar. Different guitar, different strings, but you can play any guitar. You can play, 2 people with different guitars, and they can play a duet. It's fine. You can do a wonderful job. Now here's what the periodic table Here's the one cell, the gold block. Okay, there's in the periodic table for every element, there's a name and a chemical symbol. And this number down here on the bottom is called the atomic weight or the atomic mass. 196.97. It's roughly 197. This number up here, the atomic number 79, that tells you how many protons are in the nucleus. So this gold, the typical gold nucleus has 79 protons. And let's see, 97 plus 21 is 118. So the typical gold nucleus has 79 protons and 118 neutrons. Okay, the periodicity of the periodic table is in the atomic number. So the sideways, so every 8 numbers that you go up in the atomic number, you get similar properties. And Mendeleev was the one that figured that out. So we compared an atom to a guitar. Each atom has different nucleus. So the strings are different. The specs for the strings are different. So you can compare an atom to a guitar, a quantum guitar. It's quantized, just like a guitar is quantized. But there's all kinds of different, so you can't have, you can't call them all guitars, but what you can call them is different instruments. Every instrument has a different set of strings, and that makes the periodic table like an orchestra. And as I like to call it, I like to refer to it as Mendeleev's orchestra. Every element is like a different instrument. And if you have an orchestra, no matter how big, if you all play right, you can get different songs, different beautiful music, no matter how big the orchestra is, if they play correctly. Here's an example. This is not an orchestra, this is just a trio. 2 hydrogens, 2 hydrogen guitars, and 1 oxygen guitar. We call it water. The polar shape of the water molecule. Yeah, it's all controlled by the same concepts that we saw up here with Carolina's guitar. DNA. Whoa. Deoxyribonucleic acid and regular ribonucleic acid. Genes. That's a huge orchestra. That's not a trio. That's like a zillions. All playing together. A multitude of guitars and other stringed instruments. Water. Water in the ocean. It's a huge, huge orchestra of a bunch of those water trios. And they're all working together. And then some guy's up here on a surfboard. Look at that. See how big that is? So you can think of that as a beautiful, exciting song played by instruments from Mendeleev's orchestra. And of course, you might be saying to yourself, boy, if that's really true, everything around me is like a symphony playing. If you think about it. And that means that the best symphony of them all is us. We're the best. The most beautiful of all. Now, we have some time. I want to do a review session. Can you guys hand out those papers? And thank you. We're going to do some clicking, and it'll be like clicking.